So this is chapter 15 on conjugated systems, orbital symmetry, and ultraviolet spectroscopy. Conjugated systems. So conjugated double bonds are separated essentially by a single bond, right? At least two double bonds separated by one single bond. This is an example of a conjugated double bond. This is in contrast to isolated double bonds that are essentially separated by two or more single bonds. Here's one in which the double bonds are separated by two or more single bonds. And so when we compare conjugated versus isolated double bonds, conjugated double bonds are more stable. So penta 1,3-diene is more stable than penta 1,4-diene. So for the conjugated double bonds, the heats of hydrogenation is essentially less than half the sum of the individual double bonds. So if we take 1-pentene and trans 2-pentene, it would be predicted to take the sum of those two heats. However, in reality, trans penta 1,3-diene has an actual value that's actually 225 kilojoules. As a result, it's more stable than the predicted by about 17 kilojoules. If we compare the relative stabilities of carbon-containing compounds, starting with penta 1,2-diene, that's the most energy, pentyne, 2-pentyne is a little bit more stable than 1-pentyne. And then we have penta 1,4-diene, this is isolated. Hexa 1,4-diene, again an isolated, and then the conjugated diene, that's the 1,3-pentadiene, is most stable. In terms of the structure of conjugated dienes, such as buta 1,3-diene, you have double bond, single bond, double bond. The C2, C3 single bond is actually shorter than the traditional 1.54 angstroms because it has this partial double bond character. The electrons, right, on your pi bonds are delocalized over the molecule, and there's this small area of overlap across the central C2, C3 bond, giving that partial double bond character. All atoms of the buta 1,3-diene are sp2 hybridized with overlapping p orbitals. Each p orbital has two lobes with the wave function indicated by plus and minus. These plus and minus signs are not electrical charges. When the lobes overlap constructively, that is when you have plus and plus or minus and minus, a pi bonding molecular orbital is formed. When the lobes overlap destructively, when they take opposite signs, you get a pi antibonding or pi star molecular orbital. And this is shown here. If we look at ethylene, and these are pi. So if you have the plus and plus overlapping, this will have a constructive overlap. This will result in a pi bond, right, where they're interacting with one another. Here now the signs are opposite to one another. As a result, you have what is called destructive overlap. This will result in a node in which the opposite charges repel. This will lead to a pi star antibonding molecular orbital, as depicted here and also shown here and over here. For the conjugated system of buta 1,3-diene, the lowest energy is shown here, where all of the plus signs are on the same side and all the minus overlaps are on the same side. This is a interaction. They have bonding interactions shown here. So all of them interact with one another, and as a result, the electrons are delocalized over these four nuclei. There's the pi 2 molecular orbitals for buta 1,3-diene. in this case, you have two bonding, right? So these are the same charge, these are the same charge. These then have bonding interactions. And then you have one that are opposite charge, and this leads to anti-bonding interaction. This is a bonding molecular orbital. This is higher in energy than the pi 1, which is the previous molecular orbital, and it's not as strong. The following molecular orbital, which is the pi 3 star molecular orbital, has two antibonding and one bonding interaction, in which you have now plus minus, so this would lead to antibonding. Over here, plus minus, this also leads to antibonding, and then you have the bonding interactions, the minus minus and the plus plus interacting, so this leads to bonding. And as a result of the antibonding interaction, this leads to nodes. So there are two nodes in the system, and this is vacant in the ground state. Pi 4 star molecular orbital have three nodes because all of them have antibonding interactions. They're all of opposite signs. It's the highest molecular orbital, and it's vacant at the ground state. So if we look at the molecular orbitals for the buta-1,3-diene and ethylene, buta-1,3-diene shown here, ethylene on the right, the bonding molecular orbitals of both the 1,3-diene as well as the ethylene are filled. So you see the electrons are filled in both of the molecular orbitals. And then the antibonding ones are unfilled, or they're empty. Butadiene has lower energy than ethylene, right? So as you can see, this is lower in energy than here. And this lower energy is the resonance stabilization of the conjugated diene. So an important thing to note is that stable molecules tend to have filled bonding molecular orbitals and then empty antibonding molecular orbitals. If we look at conformations of butadiene, you have the S-trans conformer, which is shown here, right? It's in the trans state. This is more stable than the S-cis, shown here, right? These are by 12 kilojoules per mole, or 2.8 kcals per mole. And they're easily converted at room temperature. The reason why this is less stable is because of this steric interference shown here on the S-cis. The allylic position, as we've talked about last semester, is shown here, where you have right next to the double bond the carbon attached to it is the allylic position. So here are examples: allyl bromide, allyl alcohol, and allyl benzenes. These allylic positions are, when they form cations, are stabilized by resonance. Allylic cations, so here if you take allyl bromide and the bromide comes off, you form a cation shown here, and it undergoes resonance stabilization, in which you have the electrons from the double bond move over, and then the cation move over from here to here. So these are in brackets, and the double-headed arrow, as we've seen before, denoting resonance. You can have resonance stabilization of even substituted allylic cations, and as well as cyclic versions. In terms of stability of carbocations, methyl is least stable, followed by primary. That's followed by secondary, which is equivalent to the allyl, and then the tertiary, which is equivalent to the substituted allylic. So the stability of a primary allylic is equivalent to a secondary carbocation, and the stability of a secondary allylic is akin to a tertiary carbocation. So you can add two conjugated dienes either at the 1,2 or the 1,4 position. So electrophilic addition to double bonds produces a more stable intermediate For conjugated dienes, the intermediate is a resonance-stabilized allylic cation. As a result, nucleophiles can either add to carbon 2 or 4, both of which have the delocalized positive. So to show this, here's a diene in the presence of HBr. So HBr is going to add to it, and you're just adding 1 mole of HBr. So it can add. First, the electrons take the proton from the HBr and then kick the electrons to the bromine. So then you form a carbocation. The carbocation that's being formed is the carbocation first on this carbon, right? But then due to resonance stabilization, if you have resonance stabilization, your carbocation can also form on this side. Sorry, and I'll show you that in the next slide to make it clearer. So as a result, you can have Br adding on this carbon right here, or Br adding on this carbon over here to form the 1,4 addition or the 1,2 addition. So if we look at the mechanism, here it is, electrons, right, go and pluck off that hydrogen from HBr, kicking off the Br, so then Br is left around here, and then you form the carbocation. This undergoes resonance, right, the brackets and the double-headed arrow, in which the electrons then move to here. When the electrons move here, your now positive charge moves from here to over here. So if the adds to the 1,2 position, right, it'll form here. If it adds to the 1,4 position, it'll form over here. Now this leads me to talk about the kinetic versus thermodynamic control. So if we take this reaction with HBr, and if we do the reaction or perform the reaction at low temperatures, you can have both the 1,2 and the 1,4 product, as we had talked before, but you can see a predominance of the 1,2 product by 80%. So at low temperatures, it prefers the 1,2 product 80%. Now if you raise that temperature to 40 degrees, now the preference changes, in which you have it prefer the 1,4 product by 85%. So if we look at what's happening, we're starting off with the intermediate, that delocalized carbocation, a little carbocation. If we're looking from this central point and going to the right, this side is going to show the thermodynamic control. Now, in thermodynamic control, the energy state of the 1,4 product is actually more stable than the 1,2 product. However, the activation energy is much higher than the activation energy for the 1,2 product. As a result, you need heat to overcome that barrier. Here's the transition state, but you attain the more stable compound. In the case of the kinetic control, the activation energy is much smaller, so as a result, it'll prefer to react and form the 1,2 product. However, the 1,2 product is less stable than the 1,4 product. As a result, it's formed faster, but it's not necessarily the most stable one. So the transition state, so this is looking at kinetic control. Transition state for 1,2 addition has a lower activation energy because it's more stable carbocation. 1,2 will be faster addition at any temperature. Nucleophilic attack of the bromide on the C2 allylic carbocation is irreversible at the low temperature. The product that forms faster predominates, which is the kinetic product, and because kinetics of the reaction determines the product is said to be under kinetic control. Thermodynamic control, 1,2 addition is still faster addition, but at 40 degrees the bromide attack is reversible. This is important, right? So at elevated temperatures the bromide attack is reversible. 1,2 product ionizes back to the allylic cation. At 40 degrees then equilibrium is established, which favors the more stable the most stable product in this case. The 1,4 addition is the most stable product, thermodynamic product, because it has a more substituted double bond, right? And because the thermodynamics of the reaction determines the product, the reaction is said to be under thermodynamic control. Allylic radicals. These are stabilized by resonance. Radical stability follows as such, where primary is the least stable, then followed by secondary, tertiary, and then the primary allylic is the most stable. Substitutions at the allylic position competes with addition with double bonds, so they're competing, so substitution of allylic positions competing with the addition. And to encourage substitution, you use a low concentration of a reagent with light, heat, or peroxides to initiate the free radical. In terms of mechanism of allylic bromide, so I'm going to draw Br. As you had seen before, in the presence of light, you're going to homolytically split that bond, shown here. I'm showing half arrows to show that, to generate 2 Br. So now you have propagation occurring, where you have Br and your molecule of interest, so the allylic hydrogens then become the target here. So you have electrons from the Br come in. So the electrons from the Br come in, and with a half arrow, form a bond with a half arrow from the homolytic cleavage of the bond right here, the CH bond, allylic position. This forms a radical, shown here. This undergoes resonance, in which you have electrons come in and move down. As a result, this radical moves up over here. And so now you have the allylic radical, and then reacting with Br2. So I'm going to draw Br. Please bear with me. So in this case, you have your electrons from your radical come in, electrons from this radical come in to form that bond, and then regenerate the bromine radical, as shown here. And then you have termination steps, which you should remember from last year or last semester. So bromination using N-bromosuccinimide. Here's N-bromosuccinimide. In the presence of HBr, will generate Br2 and succinimide. It provides a low constant concentration of Br2, right? And it reacts with HBr byproduct to produce Br2 and prevent HBr addition across the double bond. Allyl system. So the geometric structure of the allyl-cation, allyl radical, and allyl anion are the same, right? It's showing this. There's 3 p orbitals of the allyl system. They're parallel to each other, allowing for this extended overlap between C1, C2, and C2 and C3. So in terms of resonance stabilization, here's your Br radical reacting with the allylic position. Again, now the radical resides on that carbon, shown here. And then you can have resonance stabilization, in which the electrons move so that you have the radical either on this carbon or this carbon. And then both of them are equally reactive, so that you get an equal mixture of the bromine either being at the 1,2 or the 1,4 position, added at the 1,4 position. So you have either the possibility of either radical being formed, unlike the thermodynamic and kinetic control that we talked about in the previous case with cations. So here you have allylic anions. Now you have a negative charge on the carbon, shown here. That negative charge moves here to this to form a double bond, and then kicking off the electrons from that existing double bond onto the carbon, and so that's what you're getting here. So the minus charge now resides on this side. This is in brackets because it's resonance stabilized, and essentially you have a delocalization, which we already know through resonance, but you have a half a charge residing here and a half a charge residing on the other side. The allylic anion has 2 electrons now in the pi2 molecular orbital, As with allylic cations and radicals, the allylic anion is also resonance stabilized. And so if we look at the molecular orbitals for the allylic species, here's the energy of an isolated p orbital. The bonding would be if all of the positive charges are overlapping, so you have bonding occurring. So this is bonding pi 1. This is a non-bonding interaction, so we've talked about antibonding, but non-bonding is new. So non-bonding, you have plus, and then this is now not shown, and then minus. And so now you have a node that's right between these two non-bonding interactions. And then you have anti-bonding, in which now you have that, right, positive and minus, minus positive, so these are of opposite signs. So then you have nodes here, and you have the anti-bonding interactions. In the case of so allyl radical would be the neutral version, and the allyl radical, you have 3 electrons, right? So that you have 2 electrons residing in the pi 1 bonding, 1 electron in the pi 2 non-bonding. In the case of allyl cation, that electron is missing, right? So you are going to have only 2 electrons in the bonding p1 or pi 1. And in the case of the allyl anion, you have 2 electrons and another electron being added over here, residing at the non-bonding state. In all cases, the pi star antibonding doesn't have any electrons residing in it. So this ends the first part of chapter 15.